Hello, Aaron. This work is talking about building extraction by gated graph convolution neural network with deep structured feature embedding. Building footprint information is an essential ingredient for 3D extraction for urban models. Manual extraction of buildings from optical images is time-consuming and difficult for large-scale practice. Semantic segmentation is the efficient way for this task. With the modern development of deep neural network and the computational power, the semantic segmentation accuracy has been significantly improved. In particular, convolutional neural network is a powerful tool for semantic segmentation. However, one central issue remains, which is precise delineation of boundaries. Deep architectures generally fail to produce fine-grained segmentation with accurate boundaries due to progressive downsampling. In this work, we introduce a generic framework to overcome this issue. Before we go into the details of the proposed framework, firstly, I want to briefly introduce the graph convolution network. Now we have a graph G and its Laplacian L is equal to degree matrix minus adjacent matrix. If we want to do signal processing on graph, first we do an eigenvalue decomposition of Laplacian. Here phi is the eigenvector, so the Fourier transform and the convolution of signal f on graph is equal to following equations. Now we need to consider how to construct G hat here. One way is in spectral domain. If we use first order approximation, the simplified layer 1 GCM can be written in this way. Now I will show the flowchart of the SFV GDCM framework. The framework has two parts. One is deep structure feature embedding, another is gated graph convolutional neural network. In general, this framework can be used for any data, structured data, unstructured data, vector data, point cloud, raster data images. Since our input is image, we can consider it as spatial graph, which all the nodes are on the grid. Therefore, for feature embedding here, I use more efficient method, deep convolution network. One can also use other graph embedding technique for vector data. After feature embedding, the feature vectors are fed into GDCM. The initial hidden representation of the corresponding node is taken from the feature vectors of the SFV step. For a certain time step t, the messages from neighborhood of the node are aggregated by using GCN. After that, the hidden state of next time step t is updated by gated recurrent units, which use the hidden state at-1 and the message layer t at time step t. After final time step t plus n, a negative log likelihood loss function is computed, and the whole SFV GDCM model is updated using backpropagation. So for demonstration and validation, we use PlanetScope data, which is 3-meter resolution with 4 band. 48,000 patches are generated for, and 80% for training and 20% for testing. The predicted result is compared with OpenStreetMap. Here I will show our experimental results. We compared with different neural network architectures and recent graph models. For the evaluation, we use 3 metrics such as overall accuracy, F1 score, IOU. As one can see, our results outperform other methods, and also the visual result confirms the quantitative comparison. At the end, I will show 2 real applications. One is building extraction at Cairo, Egypt. As you can see here is the optical image. This is extracted building footprint. And another example is change detector after explosion in Beirut. This is before the explosion, and this is after explosion. Now we can get the change detected. So the conclusion of this work is spatial information can be efficiently propagated by the proposed framework, and the additional spatial information from short and long distance enhanced the segmentation result. And this framework has potential for different applications.